All right, mic works. And let's see if I can put it. Test, yeah. And mic is probably not needed. All right. Just wait for 5 more minutes. Let's see what this mic is. Try this out.
Hi, welcome to the
Try this out. Yeah, it's working, I guess, but not much use. There we go. I think we'll wait for 5 more minutes in case more people show up. Yeah. Huh. Is this going to be the expected strength, or should I wait for a while longer? Any idea on how many people showed up for the last recitation? About this much? I guess YouTube streaming is popular. All right, I guess we could probably just get started, and hopefully if people come in, they can catch up. Okay, so today's recitation, I will be going through hidden Markov models, start off with an introduction of HMMs, to represent what the graphical model is, the parameters, and then the problems that we're interested in solving. So whenever we talk about an HMM, there are certain things that we want to do, certain things that we want to learn from them, discuss a bit about that. And then we will go through the first of those problems, which will be used for the Baum-Welch algorithm, which is the EM technique that one can use to find the best parameters of a hidden Markov model. So let's start off with a basic picture of what a hidden Markov model is. So for an HMM, you have basically two parts. You have the observations, which we have access to. So you have a set of observations that you see. So this could be something like you measure, once every time step. You set a threshold for a time step, and you measure observations every time step. So that is what we know here, shaded in gray. Those are what we know, and the states, which are the latent variables or the hidden variables, they're not visible. We just assume that the hidden Markov model is. We assume that these states, they don't literally really exist, but we assume that the model works such that internally it has a set of states where you go to one state, you have probability of doing an observation, and so on. So these are latent variables that are not directly observable. These are things that we just define and assume go on in the background while we make the observations. So yeah, specifications of a hidden Markov model, we have set of possible observations. I denote that with the set O, O1, O2, so on. And then a set of possible hidden states. So you have a set of hidden states, Q1, Q2, and so on. So these are the specifications of, specifications of a hidden Markov model. We use those to define the parameters of our hidden Markov model. So the first thing is the state transition probability matrix. So what is the probability that given you're in latent state I, you will next go to latent state J? So whenever we look at a hidden Markov model, at each time step, we assume that we're taking a step. At each time step, we are making a transition from one state to another. So it could be a self loop. You could stick around in the same state. So what is the probability that, at some time step, if I am in state I, the next time step I go to state J? So that we define with the state transition probability matrix. So AIJ, that's what I'm using to denote the state transition probability matrix. AIJ is probability QT plus 1 equals J. So what is the probability that given that I'm in state I at time t, I'm going to be at state J at time t plus 1. So that is the state transition probability matrix. And next is the observation probability. So we're moving along in our states. So we're at each time step we're in some state or the other. But there's these observations that we can observe in the real world. So we would also like to be interested that, okay, if internally I'm in some hidden state I, did it define it? Yes, if I'm in some hidden state I and I see an observation O. So this observation O, you see it in the real world, and you'd like to know what is the probability that, if suppose internally I'm in some state I, what is the probability that I'll be seeing observation O? So that is defined by the observation probabilities, which I denote with the matrix B. So this is the size of this matrix is going to be the number of possible observations by the number of possible states. So Bi of O, so this is the notation over here. I here is the state, O is the observation. So what is the probability that given at time t I'm in state I observe an observation O? So that's how we define our B matrix. And then the starting state distribution, which essentially, so I have to start somewhere, right? So in a hidden Markov model, we have this concept of time steps. So we start at some state and we keep jumping around from one state to another. So what is the probability that the first state I'm at is going to be some state I? That is defined by pi I over here. So pi I equals Q suffix 1. So notice the 1 over here. We don't have a T anymore. Q1 equals I. So the parameters we're just gonna use some shorthand notation to just call the parameter. So whenever we use lambda to denote the parameters a, b, and pi. So whenever I say probability of O of an observation sequence given some lambda, it means that I've defined the parameters. What is the probability that I'll observe this observation sequence given these parameters? So that's just some shorthand notation. So there are a couple of things that might seem confusing over here. Why are we only interested in, if I want to know where I'll be in the next state, why am I only interested in the current state? Why not? Sorry?
Was matrix B or parameter B, was that parameter C?
In the lecture slides, I could probably dig that up. Hold on a sec. Let's take a look at that. Maybe I should have gone for same notation, but yeah, this one over here. So A, okay, so looks like A is the transition probability matrix. That's the same as what we have in my slides. And C over here, so 3 states, right? But we have 2 possible observations. So yeah, there we go. This is a 2x3 matrix. So yeah, this is the B vector. So the B in the recitation slides over here. So that is the C that Jeff defined in class. Yeah. So yeah, going back. So we have a couple of assumptions that we make in a hidden Markov model. So the first thing is the Markov assumption. We're looking at the first order Markov assumption, where if I want to know the probability that I'm going to be in some state J in the next time step, it only depends. Well, given the current data, if I know where I am right now, that's all the information I need to know where I'll be in the next time step. So given the present, the future is independent of the past. So if you look at probability qt plus 1, where I'll be in the next time step, if what is the probability that I'll be in state J in the next time step, given where I am right now, the previous step, and so on. So that is simply going to be probability qt plus 1 equals J, which is probability I'm going to be in J given that I'm in I right now. So this is a first order Markov assumption. You could maybe generalize it to you can define it to be such that the probability that I will be in state J in the next time step could depend on the previous K observations. So that's going to be a K order Markov assumption. As in, we will only consider the previous K observations, not observations, states, only the K recent states in my memory are important to determine where I'm going to end up next. So that's the first assumption. And the second assumption is that the stationary assumption, so if you notice over here, we define Aij, Bi, and we have this T parameter over here, but I didn't mention anything about, what is T? Is it 0? Is it 1? Does it have a range or anything? So that's where the stationary assumption comes in, that it doesn't matter what time step we're at. The stationary, the transition probabilities, the observation probabilities, they're independent of the time step we're at right now. So if I have something like, so this is the transition probability that at some time T, I'm at I. So given that I'm at state I at some time T, and probability that I'm going to move to state J at time T plus 1. So that is going to be the same as, probability if at some time T plus S, I'm at I, and T plus S plus 1 is going to be J. So that's the stationary assumption over here. And the last one is the observation independence. So if you look at the graphical model over here, okay, we probably haven't covered graphical models in the lectures yet, but essentially, if you take any observation, let's say we take the third observation over here, if we were to know which state we're in the third time step, that would be enough information to determine the probability that we would see the observation. So if I know which state I'm at right now, I don't have to worry about what the previous observation was or what time step I was at before in order to determine the likelihood of seeing an observation. So that's just probability that, OT, observation at time t, given, current state, previous observation, previous observations, that's going to be equal to probability of, current observation given current state. So these are the three assumptions that we have for a hidden Markov model. Let's see over here. So, okay, so we've defined this this model, and we're interested in answering some of the following questions. So, probability of occurrence of a given observation sequence. So, so the idea is, I've given you a hidden Markov model, and I ask you, let's say we model the states of a robot in a grid world or something like that. So, and then I give you observations. That observation at each time step could be something like the position of the robot, like which grid it's in. So if I give you a set of observations, and if I give you a hidden Markov model, will you be able to tell me that, okay, this observation sequence seems pretty likely. So based on the model that we've defined, it is possible that your robot would take these sort of steps and would experience these sort of observations. So that's the first problem that we're interested in. And optimal state sequence to provide an observation sequence. So so as we've defined the observation probabilities, it is possible, well, theoretically, it's possible to observe anything in any state. The probability might be 0, but so there could be several possible sequences of states and state transitions which could result in you observing a given observation sequence. So we might be interested in knowing what is the state sequence that maximizes the chance that I'll be observing this probability. So that's the Viterbi algorithm that Jeff described briefly in class yesterday. We won't be going through that in this presentation. The one we're interested in is the next one. Okay, so what are we doing in this course? Machine learning. We're given data and we have to learn an optimal model. So you're given a set of observations and you have some idea about what your HMM looks like. You know what the states are and what the latent states are and what they represent. But you do not know what the observation probabilities are. I mean, you don't know the probability that your robot is going to detect something as hot, given you're in state as 5. So we have no idea about that information, which is what we would like to determine. So we run our robot in the real world, get a load of data, and then use that to determine the optimal parameters to essentially train our model. And an algorithm to do that is the Baum-Wilch algorithm, which runs with the expectation maximization principle, which was talked about a couple of lectures ago, I think, where you would start off with an initial model, you would perform the expectation step and the maximization step, which we'll get to in later slides. So first off, let's look at solving the first problem. So probability of occurrence of a given observation sequence. So okay, should be. So let's start off with a naive solution. So a naive solution here would be, let's assume that there is some state sequence. For now, we have a given observation sequence, which is O1, O2, O capital T. So this is a T time step observation sequence. Let's assume that there's some state sequence Q1, Q2, QT. So the probability that you will observe this observation sequence given this state sequence is going to look something like this. So the independence assumptions and the chain rule eventually help us in obtaining this this form where you can just multiply the individual observation probabilities. So we're given that this is the state sequence, so you don't have to worry about the transitions over there. So yeah, the form for P of O given Q, and lambda over here is a set of parameters, A, B, and pi. So this is going to be equal to probability that I'm in Q1 and I observe O1, probability that I'm in Q2 and I observe O2, and so on. You go all the way till the last time step T. And then you have probability of Q given lambda. So we're looking at, okay, what is the probability that I just see this particular state sequence? Let's not consider the observations or anything for now. Let's just take a look at the state sequence. What is the probability that I observe, or that this state sequence occurs? So that would be, you would start off in the first state, then you would transition to Q2, transition to Q3, and that order continues, which is what we get over here. So we start off at Q1, and then from Q1 I transition to Q2, Q2 and Q3, QT minus 1 to QT. So we want all these events to occur, and so we essentially just multiply the probabilities. It's an intersection, independent events, we multiply the probability. So this is probability of a state sequence given our model. So yeah, so our original question was, what is the probability of observing an observation sequence given the model? So that will be equal to, we're doing conditioning over here. So we look over all possible state sequences and multiply the probability of that state sequence times the probability of observing that observation sequence given the state sequence. So that's just a law of total probability. We did that because we have a neat little form for P of O given Q, and so this is one way we can obtain the probability of a given observation sequence. But again, this is a naive solution. So does anyone see what the problem could be here? Why could this not be a great solution? Does anyone have any idea? So the Q over here, how many possible paths can we have? How many possible state sequences can we have? Let's say there are S possible states that Q1 or Q2 or Qt can take. In that case, the total number of possible state sequences is going to be equal to S power t. So you have to look at S power t possible paths. You have to compute the probability for each one of them, and then you have to finally sum them up. So this is computationally expensive, which is why we go for the, we have recursive algorithms that build one step at a time. So there are two algorithms, the forwards algorithm and the backwards algorithm. Let's go with the forwards algorithm, where we define a forward variable, alpha t of I, as probability of, so we're still interested in this entire observation sequence, so we're just breaking it down into chunks. So let's just look at small t steps at a time. So probability O1 to OT given QT equals I. So essentially this means that okay, all I know right now is that I am currently at time t, I'm at state I. What is the probability that I would have observed O1, O2, and OK? OK and OT, which is what we're looking for over here. So this can be computed recursively. So let's start off with the initialization. Alpha 1 of I, what does that mean? We're at the initial time step, and we're at the initial time step, and so at the first time step, so t over here is 1. So at the first time step, given that I am in state I currently, what is the probability that I observe O1 and O1 because t equals 1. So what is the probability that I observe O1 given that I start off at state I? So that is going to be pi I times, so this is the starting state probability, times bi of O1, which is the observation probability that, okay, I'm in state I, what is the probability that I see observation O1? So that's the initialization, and then okay, we define a recursive formula over here. So there's got to be brackets here, but I'll correct that when I upload it. Okay, so alpha t plus 1 j. So at time t plus 1, I'm at state j. What is the probability that I have observed O1, O2, so on, OT? So we define that recursively. So let's take care of the first part that, okay, I'm in state j. So I have to observe OT plus 1. So let's put that probability out. So probability that I observe OT plus 1 given that I'm in state j. So that part's done. What do we do now? We have information about alpha t of I. So using that, can we, maybe find out using alpha t of I. Alpha t of I has information until the last time step that we observe O1, O2, OT, and we end up at some state I at the t time step. So we're now interested in t plus 1. So what we would do is we look at all possible states from which we can transition. We look at what the probability of that, we look at the alpha values in that previous state, and then multiply that with the transition probability. So we're varying I over here. So we're first looking at transition probability. Okay, so let's say my previous state was state I. Then I'm going to go to J with Aij probability, and the probability that everything in the world was right before. When I say that, I mean we have observed O1 and OT before and end up at state I. What is that probability going to be? Because we have two things over here. We have to transition and end up in state J, and at the same time, O1, OT, that has to be preserved as well. We have to observe that particular state sequence, that observation sequence. So we multiply alpha t of I with Aij and sum it up over all possible values of a state. And that's going to give us alpha t plus 1 j. Yeah, and in the end, when we want probability that of an observation sequence given the model, we just go. So we look at all possible states that I could end up in, and then sum it up. That we have multiple possible paths, right? So okay, if I ended in state I, what is my, let's say I know that I've ended in state I, what is the probability of this observation sequence? That's going to be alpha t of I. So I look at all possible states, add those up, and that's going to give me probability of observing this observation sequence. So is the forwards algorithm clear? Or?
So when you do the summation, so alpha t, capital T,
yep.
You mean?
That's the last time step.
The last time step?
Yep.
So the last time step with all the previous states.
So I've already observed everything. I've observed everything, and now I've ended up in state 5. That's essentially. Okay. Yeah, so you can look at it, alpha capital T of I. What does that mean? It means that I've observed O1, O2, O capital T, which is my observation sequence, given that I've ended up in state I. So we could just, it's essentially going to be conditioning. So let's see, I could probably write that down over here. So we're interested in this one, right? O1, O2, OT, given lambda. So let's just condition this on the last state. Given qt, let's say this is equal to some I lambda. Again, just applying the total probability theorem. Qt equals I. Yeah, we just vary this from I goes from 1 to all possible states. So it's going to be alpha t of I, and this part is not clear. Wait. Yeah, hold on. Ignore this part. I think this is slightly incorrect. I'll write this down again later, but for now we can ignore it. Sorry. Well, essentially, it's like a yeah. It's just you have some possible events that you could either end up in I or J, or so these are independent events, and you just sum those up. So it's like a union probability. The intersection they're independent. So yeah, so the intersection. Yeah, so it's like a union probability. What is the probability that I see this observation sequence and end up in state I or state I plus one, either state 1, 2, 3, S. So the intersection of these events would be phi, because you can't end up in multiple states at the same time step. So essentially, the union probability, if you apply the union probability theorem, it would just be the summation of this alpha t of I. I could probably formally write it down later, but yeah. This should be backwards variable. Sorry about that. So then there's the backwards algorithm where we look at things in reverse, where we define the backward variable beta t of I to be probability that I observe from this point on. I observe everything correctly, given that I start in state I. So probability OT plus 1, OT plus 2, so on until OT, given that QT equals I and my lambda. So I'm in state I. What is the probability that from here on I'm going to observe everything correctly? So that's what we define. And we initialize beta t of I equals 1 because, well, I'm definitely we've already observed everything. So if you notice over here, this is capital T. So we're interested in. So if we look at this formula over here, we would be looking at OT plus 1, which doesn't make sense. So we define this to simply be 1. It's equiprobable initially that no matter starting at this state, I don't care about what I observe. So we define it to be a uniform distribution, and so just define it to be 1. So yeah, so the way, so the recursion that we define over here is going to look something like this. So okay, so now I'm interested in looking at at time step t, I'm at state j. What is the probability that I'm going to observe, OT plus 1, OT plus 2, and OT plus 3? So again, similar to the forwards algorithm, we look one step in our direction. So we look one step forward over here. So I'm currently at state. So we look at all possible. So I'm currently at state J. So I could go to some other state I. So we sum over all possible states I to which I can transition to next. We multiply the transition probability. What is the probability that I'm going to transition from my current state J to the next state I? And we multiply, let's say I do end up in I. What is the probability that I'm going to look at that? What is the probability that I am going to observe OT plus 1? And then we multiply the backward variable in order to complete the recursion. So I'm at a current state J. What is the probability that I'll move to a new state I? That's going to be the transition probability multiplied with the probability of observing the right thing. And then from next step onwards, everything else runs smoothly. That's encoded by the beta variable over here. So this is how we define the backward variable recursion. And then in the end, we would just, similar to the forwards algorithm, we would look at beta 1 of I. So what is this? At the first time step, I start off in some state I. What is the probability that I will observe the right observation sequence? This is what we define our beta variable. Okay. So is this part clear? Yeah.
Why do you not need to include pi at the very end?
Uh,
You mean like the initial distribution?
The initial distribution. Okay. Oh, over here. The probability that you start off in this state, right? So what would this be? Probability that I initially start off at state I, and then Right? So let's see, what is beta 1 of I? Beta 1 of I is going to be what? I start off at this state and I observe the right observation sequence. Would this be beta 0 maybe? Yeah, I think you're right. There has to be a pi. I think we have to go maybe one step further, because beta 1 of I over here is probability that I start in this state and observe OT plus 1 from O2 onwards. So it's probably going to be something like beta 0 of I, or if I do have beta 1 of I would probably have to multiply the first observation probability and the starting state probability. So yeah, I think there's a bit of correction over here. I will, correct this when I upload the slide, but yeah, your pi has to be factored in here. I will, sorry about that. Yeah, but the general idea of the backwards algorithm, I think, is clear, right? Apart from the end step, which seems like it should include a pi term, I think apart from that, the general idea seems to be clear. Right? Cool. So okay, so let's look at the Baum-Balch algorithm. Okay, so now we're given a set of training data. We want to, so we now have a set of data, and we want to estimate parameters of our model that maximize the probability of observing this data. So essentially, we want to train our model given this data. We do that using the principle of expectation maximization. So what do we do over here? So in the expectation step, so we have this data. So given our observation sequence, we compute the probability of transitions to a state. Given these observation sequences, probability of observing this observation sequence. We do that in the E step, and in the M step, we recompute our parameters using the calculations that we perform in the expectation step. We define a couple of terms in the expectation step, which will probably be clear. We do this until convergence. So more in detail to be so we define this variable chi t of ij, which is probability of being in state I at time t and at state j at time t plus 1. So we're looking at time step t and some time step t plus 1. What is the probability that I'm going to be at I and then I'm going to transition to j? So this is different from the transition probabilities where we defined it to be stationary. Over here, we're interested in the particular time step. We have these observations, and given these observations, what is the probability that this particular transition, that state I at time t and state j at time t plus 1 could have occurred. So the time here is important. And previously, when we defined the state transition probabilities, we didn't worry about the time t. But in this case, when we define chi of ij, as you can see, t is another argument to the function. So time t over here is important. So okay, how do we define that one? So let's just write it out. Probability that I'm at time step I, at time step t, I'm at I, and then I move to j in the next time step. So again, just using just conditioning. Using conditional probability, we get probability of observation sequence, and this probability that I see this observation sequence, and probability that at qt I'm at I, that qt plus 1 I'm at j. So what is this going to look like? So we write this as alpha t of I. So if we go back to the definition of alpha, what is alpha? Probability that I observe O1 to OT, and then I land given that I land in state I. So probability that we observe O1 to OT, and we're currently at state I. So that's encoded by the alpha term over here. And then we have to make a transition. So let's multiply the transition probability, Aij. So we transition from I to j. That's what we multiply over here. And then what is the probability that we observe? So let's look at the definition of beta first. Beta we define if at state if at time step t I'm at I, I'm interested in the observations from time step t plus 1. So we define beta t plus 1 of j over here, which means that at time step t plus 1, I'm at j, and I observe ot plus 2, t plus 3, and so on. So we have to factor in the observation at time step t plus 1, which is why we multiply the observation probability over here. So we multiply the alpha variable, the alpha variable, and then, so this is going to encode everything that we've observed until time step t. What is the probability? So this is, I've observed everything at time step t and end up at state I. What is the probability that I'm now going to transition to j? And given that I'm in j, what is the probability that I'm going to look at that assumption, that observation, ot plus 1? And from that point on, what is the probability that life is going to be smooth and I'm going to observe everything else as it should be observed? So that's how we get the numerator, and then this is divided by. So is the numerator part clear? Part clear, right? Okay, so we're still interested in probability of observation given lambda. So yeah, so we could write this as a function of the previous one over here. So this is probability that we see this observation. So this guy over here. So if we sum up over all I and j, so that's kind of like variable elimination, where if you sum up over all I, we don't have to worry about qt anymore. If you sum up over all j, we don't have to worry about qt plus 1 anymore, and we'll only be left with probability of O given lambda, which is why the denominator over here is just going to look as a double sum of the numerator, where we vary our parameters from j goes from 1 to s, where all possible states. So is that part clear? The probability of our observation sequence, why we get this double sum. Yep. Cool. So this is how we define chi t of ij, and then we define this variable gamma, which is a summation over all ij. So essentially, what this tells us is we're looking at, okay, I'm at time step t, I'm at I. So chi over here gives us the probability that I'm at time step t, I'm at I, and at time step t plus 1, I'm at j. So if I sum it up over all j, that's going to include all instances where at time step t, I'm at I, which is why we're summing up over all j. That's going to give me gamma t of I, which is the probability of being in state I at time t. So is this definition of, does this definition of gamma make sense? Cool. Right. So this is the expectation part, where we have a model. We notice that we're not recomputing any of the A parameters or the B parameters or the pi parameters. We have a model, and we're trying to compute these probability of observing our data. We use these guys over here, and now we use these calculated terms to re-estimate our parameters. So okay, now I've factored in the fact that I've factored in my observations and got some probability that, okay, I can go from I to j at steps t and t plus 1 with this sort of probability, given that, given my observation sequence. So using that information, we re-estimate parameters as follows. So the starting state probability, what are we looking at? So gamma over here is the probability that I'll be in state I at time t. So if we want to know the starting state probability of some state I, we just have to look at gamma 1 of I. That's going to tell us the probability that at the first time step, you're going to be at state I, which is what we get over here. Pi I equals gamma 1 of I. And then the next one is our transition probabilities. Probability that I transition from I to j at any given point of time. So over here, the time step is not important. This is stationary probability. We don't worry about the time step that we're looking at right now. So what do? We sum over all t. So this guy over here is the probability that at some time step t, you're going to make this I to j jump. So by summing it up over all t, what we're essentially doing is we're looking at all possible ij transitions. So if we're looking at our data, it would be like we're looking at we're summing up over all time step t. We're summing up over all time steps t. So this would be the total probability that at any given time step I'm going to jump from I to j. So this would encode that I'm jumping from I to j. So this we didn't divide by the denominator, which is the number of times, which is the probability that we're going to be in state I. So what's this? If we can just write this out, aij is essentially what? That qt plus 1 equals j, given qt equals I, right? Mm-hmm. So this one over here, if you sum up over all t, we're essentially summing up this probability over all t. So that's going to be our, chi t of ij or gamma. So if you think of it as number of samples, if you try to think of it as in in terms of the number of samples that you observe, so this is essentially telling you that, okay, I've seen my observation sequence. I am summing up all instances where I jump from I to j, and I'm going to divide that by all instances where I'm at time step I, and that'll give me the probability that I jump from I to j. Yeah.
For the stationary assumption,
Mhm.
Doesn't that mean that every chi t is going to be the same as every other chi t? In terms of going from I to j?
Sorry?
The top symbol,
Mhm.
t, isn't that going to be the same as every other? That because of the stationary assumption?
So you're saying that chi t over here doesn't depend on t? Is that what you're?
Yeah.
Yeah. So that's when one main difference between. So this is, notice how we defined this. So when we defined aij, we defined it as the probability of jumping from I to j. We never mentioned anything about time. But when we define chi t of ij, we define this as probability of being in state I at time t. We've defined t is important over here. This is how we define the variable. That we are at a time t, and we are at a state I, and then at time t plus 1, we end up in state j. So we define, so if you notice this parameter over here, we have t is also an argument to this function over here. So this is how we define chi. We take into consideration the time step as well.
Okay. But does the stationary assumption not just assume that that's going to be the same?
The stationary assumption, yes, the stationary assumption comes into picture when we look at the transition probabilities. So this one over here, we're not, okay, I see where your confusion can be coming from. So this one over here, we're looking at our data and we're trying to get empirical estimates. Like we're only looking at time step t, and we're looking at, in my set of samples, how many times I see this ij transition only at time step t. So this is not a parameter of the model. Which is why the assumptions, they don't hold anymore. This is just some term that we've defined for our empirical calculations, which we later use to re-estimate parameters of the model. So this is not a parameter of the model, which is why, yeah. So the stationary assumption is because the way we defined Aij is that it doesn't depend on the time step. But that's not how we define chi over here. We define it to be dependent on the time step t. Yeah. So you can think of it as chi t essentially looks at only the time step transition from t to t+1. So it only focuses on that one particular interval, looks at all ij transitions. So when calculating the stationary, the transition probabilities, we sum up over all possible time steps, and then we divide by all possible time steps. So this is going to be let's say I've observed 3 transitions at time 1, 2 transitions at time 2, 10 transitions at time step 10. We sum up over all those guys, and then we divide by the number of times that we were actually in state I for all time periods. So over here, we're getting rid of the dependence on time when we recalculate our transition probabilities. Yeah. So that's how we define our transition probabilities, and then our observation probabilities. So what's that going to be? The probability that I'm at state I right now, and I observe some observation O. So what do? We look at all instances where I was at state I, and I observed an observation O, and I divided by all time. So let's say I observed observation O when I was in state I like 50 times, and I was in state I throughout the HMM like maybe 600 times. So the probability that I would observe this observation given the state would be 50 by 600. So that's what we're defining over here. So the numerator, it only looks at all observations where gamma t of I. So one important clarification over here is, so this is for a given observation sequence. So when we have a data set, we would have like several observation sequences. So we would be looking at all possible things over there. So here we go. So we would be looking at all sequences where all time steps. We would be looking at all time steps where my observation was O, and my current state was I, and then we divide it by all the times whenever my current state was I, which is represented by the gamma variable over here. We're summing up over time to remove that dependence on time. And then in the numerator, we're only looking at specific instances where my observation was actually O. And then we sum up over Z. So that's the maximization step, where, okay, we've computed these parameters, we've computed some terms, and used those terms to re-estimate our parameters. Now, the next step would be use these guys, plug them back in here, compute chi and gamma again, compute your estimates again. You would continue doing that until they converge. So that's essentially what we do with the EM algorithm. And yeah, so that's at the end, you would have your well-trained hidden Markov model. So that's essentially the EM algorithm. And yeah, so any questions on that? I guess then we're, oh, I guess that's it. I guess we're done then. Cool.